So the title of my talk is about birational equivalence of cerebral varieties. Here the author proves a version of the so-called Amitsur conjecture for a special case. So before I write down the main theorem and uh, the proof of it, let me just go through the background. So I'll start with the most important object uh, for the talk today, that is the cerebral variety over a field K. So throughout little k will denote a field for me, and so a projective variety, so x, a projective variety over k, such that when you base change x to some separable extension, a finite, then if it becomes isomorphic to Pn, then x is called a cerebral variety, which I will denote as SBV of in shorthand notation. Okay, over K. So in fact, it's equivalent to check for when you base change it to the algebraic closure of K or separable closure. And so, so we call a cerebral variety to be split or trivial if it's already isomorphic to Pn, and a cerebral variety is split or trivial if and only if X admits a K rational. So split over K admits a K rational. So there is a parallel theory in terms of algebra and in terms of geometry. So the algebra side and the geometry side. Uh, in the geometric side, you have the cerebral variety. In algebra side, you have the central simple algebra. So there's a bijection between them that given a central simple algebra of dimension n square, you will get a cerebral variety uh, A, or say P corresponding to A of dimension n minus 1. Okay. So here for example, this will correspond to Pn. Okay. And in this case, a central simple algebra is called split if it's isomorphic to matrix algebra. So now this central simple algebras under tensor product forms a group, forms the Brouwer group of K. And so it's abelian, which is easy to see because tensor product commutes, and its torsion, well, it's not so easy to see, but there is an equivalent description of Brouwer group in terms of this second Galois cohomology, which is basically uh, in every element here is a finite order. It's a torsion. Okay. So we will give a description of this operations in geometric site as well. So, but for now, let's write the theorem of Amitsur, which tells that if P is a Severibov variety over K, then you look at this base change map and kernel of it. So this will be generated by, so by the way, for a Severibov variety P, I will denote the square bracket P for the corresponding algebra. So one thing to note here that obviously class of P lies in the kernel, because when you base change P to its function field, there is always a KP rational point. So one side is there, but it's actually an equality. So an easy corollary tells you that if x and y are birational, Then there are classes in Broward group. If I denote with this square bracket x and y, then they generate the same subgroup, right? Because then birational things have the same function. So what he made, so the conjecture he made that the other direction is also true. The conjecture is suppose x and y are Savory-Brewer varieties over K such that they have same dimension and they generate the same subgroup. Then they are birational. So I will not always write. I will just give a x tilde y after some at some point of time. So firstly, you note that one weak. Uh, how should I say? So one weak version is already true that they are already stably birational. That you can easily see because so remark under these assumptions, under the assumptions of the conjecture, uh, x cross this is birational to. And how do you see it? So first of all, you base change x to the function field of y, and you do the same for y, and they then generate the same subgroup because x and y generate the same subgroup. But this is trivial because y lies in this kernel of this, the class of y. So this is also trivial. That means this is isomorphic to p n cross ky over k. Yeah. So n is the dimension of x. So then now you can now you notice that the function field of x cross y is this, and this is the function field of uh, Pn cross y over k. So then they have the same function field means they are birational. Now you can play the same game by reversing the role of x and y, which will basically give you Pm cross x, where m is the dimension of y, n is the dimension of x, n is dimension of x, m is dimension of y. So this version is true, and we'll use it at some point of time. Okay. So let me now give the main result of today's talk, which is I'm calling it as theorem one. This tells you that suppose PQB cerebral varieties over K of equal dimension such that dimension of P plus 1 is not a prime power. Then they generate the same subgroup. I mean, then they generate the same subgroup if and only if P and Q are birational. So, in fact, what we will prove is the following. By the way, this plus one is coming because when we go from a central simple algebra to a cerebral variety, the dimension drops by one, right? I mean, drops by in the sense if the dimension is n square, you go to n minus one because you're going in P. So that's why this plus one is coming just to balance things. Then, okay. So what we will do is the following. So this is the main theorem, and we'll prove something stronger, that let P1, P2 be cerebral varieties over a field K, and let this co-prime, then P1 tensor P2 is birational to P1 cross P2 cross PR, where R is the product of the dimension. So, by the way, so I have not defined what is this tensor of cerebral variety, but you can take it as so. You look at the algebras here, A1 and A2. You do the tensor product. That will correspond to some variety, cerebral. So you take it as it is. Or equivalently, one can show that it is some cerebral variety in which there is a map from P1 cross P2, such that when you base change everything to say algebraic closure, some splitting field of both P1 and P2, some common field, then that map becomes a Segre embedding. So Segre embedding is like if you have Pn cross Pm, then Segre embedding gives you P uh, to, let's see, uh, plus 1 minus 1, so which is Mn plus n plus n. Yeah. So which gives you basically if you have an xi, yj, this will just give you xi. So that's my definition of tensor of two subgenuine varieties. And just to note that Amitsur proved something similar under these assumptions that he proved that P1 tensor P2 cross P power some R1 is birational to P1 cross P2 cross this. So the author manages to remove this R1 from that theorem. Okay, so that's the key take from here. Now okay. So let's now give a quick recap of some notions of Brouwer group, some invariants attached to it. So Brouwer group. So I've already defined what it is. And so in terms of geometry, if P is a cerebral variety and Q is a subvariety, is called twisted linear subvariety. If when you base change, it becomes some copy of P, Pn, say Pm. This is Pn, such that this map becomes is a linear subvariety. It's a linear, and attached to a Brouwer group of K, there are two numerical invariants. One is the period of an element, which is basically the order of it in the Brouwer group, which makes sense because every element has a finite order. And other one is the index. So index, there are equivalent definitions. In terms of algebra, every element in the Brouwer group is min of D for some division algebra. You take the degree of the division algebra. If that is Brouwer equivalent to D division algebra. Or equivalently, you can take the GCD of degrees of splitting fields. So GCD of K splits the class. So both are basically equivalent. So the fact is that period always divides index, and period and index share the same prime factors. Okay. That's about the preliminaries. Now we'll record some known results about these twisted linear subvariety and related things. So let me just record these things uh, which the author mentions in his paper. So it says, firstly, let me write it as a lemma, say one. So, so by the way, every Brouwer class, there is an underlying division algebra. So you consider the uh, corresponding thing in the geometric side to be P mean if P is the class. So that will be called the minimal twisted linear subvariety. Minimal in the sense it doesn't contain any other twisted linear subvariety. And obviously, then by this definition, index of P becomes dimension of D plus 1 because you're shifting it to P. So there's a minus, you have to balance it. So you get that dimension of P mean is basically index of P minus 1. And moreover, P is bidirectional to P mean cross R, where obviously R is the difference of their dimension. That's number one. And number two is a decomposition theorem, which tells you given separable variety over K, say P and Q, uh, or let's say given minimal cerebral variety, P and Q, with dimension of P and dimension of Q, this condition. That means these are basically the index because I'm taking them to many elements. So they have co-prime index. Then P tensor Q is the minimal cerebral variety in the class. So basically, all it tells you that if you have two division algebras of co-prime degree, then their product is also a division algebra. This is what it is. Basically. Okay. So having okay. So now, so the strategy is as follows. We'll first show. So basically, we'll try to prove the second theorem, and uh, then we'll. So firstly, we'll show that the second theorem implies the first one, and then we'll try to prove a proposition that will imply the second theorem, so that everything's done. Okay. So now let's first show why the theorem 2 implies theorem 1. So first, let's assume they are not minimal. So if not minimal, then by this lemma, first one, lemma 1, then you get this, and you get this. Now P and Q have equal dimension, and we'll eventually prove the theorem for minimal subvarieties. So minimal subvarietal variety. So that means P mean and Q mean will be birational, meaning they have same dimension. So eventually R and S will be same because R is the difference of the dimension and S is the difference of the dimension for Q. Okay, so it's done. Provided we prove it for minimal Sabri-Braveri. And now let's assume them to be minimal. So in that case, you have the decomposition theorem in Braveri, which basically tells you. So now assume P and Q to be minimal. Now since dimension of basically index of P has at least two factors, you can break it as this is nothing but index m plus 1 n plus 1 with them being co-prime. And then you have the decomposition theorem which tells you that you can always break an element in the Bravер group into elements. So if the index has some prime factorization pi power alpha, then you can break that uh, division algebra into product of di, where index of di is p power that thing. So in our words, this is so I will call those parts to be p1 and p2. So p1, so this will be Bravер equivalent to p and minimal because division algebra is corresponding to of index m plus 1, that means dimension m. Then p2 will be uh, Bravер equivalent to not exactly p, I'm sorry. I mean p1 is the p1 and p2 are the minimal algebra. How should I say? So any division algebra, if you break it into its prime factor, the index of that, then you can find division algebra as d1 and d2. So d1 is that, d2 is that. So minimal of index plus 1, that is dimension n. And same you can do it for q1 and q2. Minimal. So now this I'm doing for q. Minimal of index m plus 1 dimension m, q2 minimal of index. So then obviously p is this, and that means they are isomorphic because all of them are assumed to be minimal. So then now you apply the theorem 2, which gives you p is birational to p1 cross p2 cross p power nm, and q is birational to q1 cross q2 cross again p power say, mn. Okay. Now you apply that stably birational thing that uh, we discussed at the beginning to get that p1 cross p power n is birational to q1 cross p power n, and p2 cross p power n is birational to q2 cross p power n. Okay, so now we have four equations, and then now it follows basically because you can p1 write this as this thing as birational to sorry, p1 cross p2 cross p power m cross. So you can always break it. Now you apply the fourth one to get P1 cross Q2. Now you get a PM, so you can combine them. So you get this. So now so you have replaced P2 by Q2, and you can do the same thing by you can replace P1 by Q1. And this is birational to Q, this is birational to P. Throughout, eventually we get. this. So this was our main result. Okay. Yeah. So now our focus will be to give a proof of the first theorem. Okay. So the main ingredient is in proving the second theorem. The main ingredient in proving the second theorem is the notion of way restriction. So way restriction is, so in our case I will take the field extension to be finite and separable, and the varieties are geometrically integral, geometrically normal, because eventually everything is just Pn. So way restriction, so what it does is, suppose x be geometrically normal k variety, k over k is a finite separable extension, then there also the way restriction will be unique normal variety over little k, such that there, say, any k prime valued point is, this is over k, in, can be identified with the k tensor k prime value point for our extension. Okay. So one may think of this as, so this you can, okay. So you may assume this to be Galois also, finite separable, so it's simple. So you can take the splitting field, sorry, the polynomial. Yeah, basically you can take the splitting field of that element. So then basically you will get is, what you will get is, any k dash valued point of this y restriction is basically a copy of x, but along with its conjugates of this Galois extension, if you take it to Galois. Okay. So as a fact, the y restriction of, and which we'll need later, of Pn is Pr with, now you can compare the dimension. R will be, so a copy of Pn but with this. Okay, right. So now the key ingredient in proving the theorem 2 is the following, which is actually, I feel it's natural to ask this kind of question, that so you start with a Severino variety over little k, you take its base change over some finite extension, finite separable or finite Galois extension, capital K. Then you put the y restriction. So it will be a variety over little k as well. And this relation tells you that. So let me write. So proposition, which will be the key thing, is, so let P be a separable variety of some dimension k, and k be a finite Galois extension of degree m plus 1, which you can take less than. Let their coprime, then, so you consider this, that is actually birational too. So m is Yeah, M and N are defined. So this will be the key proposition. This will basically follow. This will basically imply the second theorem. And well, now let's. Okay, so first let's take this proposition for now. We'll try to sketch proof at the end. Uh, let's see how it follows, how theorem 2 follows from it. So yeah. Okay. So but before doing this, first you note some properties of uh, this way restriction. So property. So let again P be a variety over little k, k over k be a finite Galois extension. L inside pk be a twisted linear subvariety such that their Galois conjugates. So when you base change everything, all these L sigma becomes some copy of Pn inside some bigger copy of the P capital N, which is basically P is a form of P capital. So then what it tells you that this spans L. So I mean this notation is not very good because this doesn't make sense actually. Okay, but this is what the author mentions. And are linearly independent. So I guess when you base change everything, everything becomes Pn. So then I think this subspace is basically uh, spans Pn and they are independent. I think this is what they mean. So then there exists a twisted linear subbundle. So this is P. So this is the bundle over this. Such that the projection to the second factor is birational. And essentially the proof is by linear algebra. Uh, so how does it follow? Uh, so what you do is okay. So let me write the linear algebra fact. Then it will be clear. So suppose you have some linear subspaces inside Pn. So suppose span Pn. Sorry, and this. This is ensured when you base change everything by this fact that they are independent and degenerate. Let P be a general point, then so general point means it doesn't contain in any span of in many such spaces subspaces. There are n plus one. By the way. So then there exists a unique linear subvariety M Pn and n that contains P and intersects each other. Yeah. So So this proof is I'm not doing. This is linear algebra exercise essentially, and so you can do on induction on little n, because in this case, if little n is 0, you literally can take m to be the span of the single point. So obviously it contains p and also it cuts L0. Right. Okay. Now, if there are, if this is true for n minus 1 many, you take n such subspace, you fix one, so you fix the 0, and you take the projection in the remaining. Then you will get some subvariety m for those n minus 1 many things. And then you just basically add the point p to it and take the span. That will be your m in that case. Okay. So then, uh, having taken this into account, mm, let's see. So we need to define what this subbundle is. So in that case, what you do is you over a point little p, you take the fiber to be. So here over. Uh, so first of all, you let. Okay, so we need to. Okay, so we should write it properly. So here, so you take this the field extension, take this and this be a general point, prime point with its k prime over k prime conjugate pm. Yeah. Then what you do is over this p naught, you take RL has fiber over p naught to be the span of this. Okay. And now you can check the birationality of the projection to be so this will project to P naught, right? So now birationality can be verified over the base change extension. So you can take all of them to be projective spaces. In that case, this thing exactly is this linear algebra fact. And so this map, the projection map. So if P naught you take to be a general point, which is an open condition because P naught is away from the span of any such n copies of the subspace. So over that thing, you will get a unique subvariety which will cut everything. So you cut uh, every conjugate, and that tuple you put send it to P. So that is the inverse. So then this becomes birational. So okay. So now let's first see how this proposition implies the theorem, and then go into the proof of the proposition. So again, you assume everything to be minimal. So in that case, so proof theorem 2, assuming the proposition. So assume minimal let this. Then, as I said, there is a map like this. Let this be the splitting field of P2 of degree index of P2. There is always such field. That is why actually taking GCD actually, uh, yeah, so I defined it to be the GCD, right? So actually equivalently you can take it to be the minimum because there is always one such extension that's equal to the index that splits. Okay, so just as a remark. And so that means there is a point over this field. And now you take L to be. So we'll apply this proposition. We'll apply this property for that. This is over the base change capital. And so you will get something P2, which is inside this cross this, such that this projection to is birational. Uh, so now you apply the proposition to get L, which is basically P1. That is birational to P1 cross, uh, oh, let me write it in here. Birational to P1 cross P power R, where R is the product of the dimension. Okay. Now what you do, you take P1 tensor P2, you base change it to the function field over this way restriction. That will basically trivialize P1, right? Because they have the same function field. So function field of this is this with some. So when you have P1, you first go into its image inside Bravard group of KP1, right? Then you go here by the functoriality. But this will go 0 to 0 because of that actual Amitsur theorem. Not actual. So then this basically trivializes. So P1 tensor P2 and P2 itself, they are over the way restriction. They are actually they actually Bravard equivalent. And because all of them are minimal, you may take it to be this. And since the dimension of this and this are co-prime, and this is actually the degree of the extension. So when you even base change to the function field of that y restriction, still the index doesn't drop. So what you get is eventually RL, which is actually birational to P1 tensor P2, and that is actually isomorphic to this over the function field. But then this is again, if you apply the proposition, is this. So this together gives you the actual result. Okay. And now let's, in the remaining 10 minutes or so, I will just try to give a proof for the proposition. So, so the proof for proposition is as follows. So let's check proof of proposition. So you consider this M dimensional twisted linear subvariety Grassmannian of P and the universal bundle over it. This is basically a pair. P belongs to L and L is in the Grassmann. So obviously it has projection in both ways. And so firstly we note that for uh, over P, this is GR M minus 1 over bundle. So over P because why? Because if you fix a point P, so this will the fiber will be all the elements in the Grassmannian that contains that fixed point P. So that means you are basically looking at the subspaces of the quotient L of P. So that's why the dimension drops. And such a fiber, when you take, so let's call it X, that is inside uh, P, and because when you base change, this becomes actually uh, inclusion of linear things right, between two projective spaces. So the O1 pulls back to O1. So that means there is a O1 over the fiber. So which means basically that it is actually trivial. So it is Pn minus 1. And so that means this is birational to P cross M times n minus n. And now you look at the other fiber. So every fiber F of this is a Severino variety of dimension m. So it has its canonical class, which is O minus m minus 1, and it is inside P. So you take the restriction of the canonical class, which is O f minus n minus 1. Since they are co-prime, OF1 exists, which basically means that this is already trivial. So it is trivial of dimension m. So from here you get this. Uh, so combining both this, you get this. So eventually, uh, so you get this. And now the final observation, which will put everything into places. What you do is, so remember the statement. So you look at the way restriction of the base change of this. So what will actually tell you that the way restriction of this. So if you look at any k dash valued point for a extend field extension little k dash of little k, this is basically points of pk plus its Galois constant. And if you uh, take span of those things, that will be actually Galois invariant because we are taking the span. So the Galois action is basically permuting those things. Right? So when you take the Galois action, this will be Galois invariant. So it will come from a element in the Grassmannian over K prime, not over K tensor K prime for bigger K. So basically a general point. So let me write it as follows. So a general point P naught K dash together with its conjugate span a subspace say, L of P naught of dimension m, say conjugate say P naught to P, which is over K prime. So that means given such a point, you get an element in the universal bundle, and there's a k dash value point in universal bundle. You take the span and you take the k prime. And also conversely, given such a span or given a subspace, you look at the fiber. The fiber is actually PA, so you get lots of points. So over the general points, there's a isomorphism. So this defines a rational map, but over the general point, which is an open condition, you get a sort of bijection. So this is actually birational too. The Y restriction is the universal bundle, but that is because Y restriction actually behaves well with the product. So and universal bundle, if you recall from the first thing, let's use this. So this is Y restriction of this cross p power m times m plus 1. That is from the fact that I recalled at the beginning while defining Y restriction. And then now this is using this uh, 1 and 2. This is so you can break it into pm plus pm square, right? Now you use this using 2. This is p cross p mn minus m square, this plus m square. So that completes the proof basically. So yeah, I guess I am on time. Yeah,